So I'm Nada Amin, and this talk is about the work I've been doing at Midspiral to bring formal verification to mainstream. So really the practicalities of proof-driven development, when it works, when it doesn't work. And also like a lot of it is really how can we even, if we have a big development of it already, a big code base, how can we decide what is there to verify or not? And also this observation that it's really much easier to start greenfield for verification, like having verification from the beginning rather than bringing it on later. So I'll show some examples of this and some discussions around this. And I'm also an assistant professor of computer science at Harvard. And at Harvard, I do work more at the foundations of formal verification and LLMs as well. So I have some slides on this, but I think what I'll do is I'll skip to the mid-spiral part, and then if we have time, we can come back to the Harvard work as well and freely mix the two as needed. So just to start, for the motivation for this, it's really to think about like why now for verification and AI. And there's two parts to this. One is thanks to AI, we can do it. Proofs that used to take, maybe even weeks of work before now can take like a few minutes or like hours, maybe like really drastically reducing the amount of time that is needed to find a proof. And and so that really changes the bar for what we can verify now. It really makes it possible to verify more things, verify things that are not safety critical because the cost is so low. And of course, we also get an independent check, right? We get these formal tools that gives us an independent check that the proofs are mechanically correct, and we can then reduce the surface checking of of our system. So kind of thinking about just looking at what are the formal specification versus looking at exactly all the proofs, because the proofs are mechanically checked, so we don't need to do that anymore. So that's a big one. And that really goes to the other side of it. Because of AI, we need to do it. AI generates a lot of code, and maybe it passes tests, maybe it looks right, but somehow correctness is not proven. The corner cases are not guaranteed to work. And even if you test your app, you're not really sure that it's completely correct. And it's kind of crazy to have to review thousands of lines of AI generated code. So formal verification offers a way of reducing the surface checking there and really kind of offering a way to validate what the AI is generating that is different from just self-validation. So I think these two things are really bringing us together to push verification plus AI and push verification into the mainstream separately as well. And so you all know Daphne in this group, but that's I mean, usually I introduce it as like an auto-active verifier. So it has this semi-automation, which is really nice. Um, and in the work we've done at Harvard, we noticed that because of the semi-automation, it's actually much easier for LLMs to get started doing proofs in Daphne because if the proof doesn't go automatically, it's a strong signal that there's something to fix, maybe even in the code. So it's kind of a useful signal to see where things fail to fix the code. But if you're using a tool like Lean or Rock, sometimes the proofs are just very hard. So even if the proof fails, it's not really a signal in itself. You have to dig in more, have to make sure that you're using the right techniques and so forth. So that's something we found in our work. And then, of course, it's also Daphne is also used in safety critical systems or thinking about AWS authorization engine invoked 1 billion times per second. For this work, they actually ended up doing a tailored backend in Java for Daphne. Daphne already had a Java backend, but this is one that was tailored for the task, and they made it like really idiomatic and fast to do this AWS authorization. And of course, the advantage for us and of verification in general is that we can verify a piece of code for all executions, not just one. And that's really the advantage over testing. And in some sense, I can see a world where you kind of do testing or property-based testing to iron out issues at first, and then do verification to kind of make sure your system is correct before you ship to production. But I can also see a world where verification is really guiding development even more, and the constraints imposed by verification is shaping how the code should look like. So there's these two things here. And in terms of bringing verification to the mainstream, so the few things I want to mention here before we dive in is that code bases need to be designed with verification in mind. Like that's just really make things much easier. Like I think the difference really is if you don't do this, you end up being able to prove kind of local properties of your code so that this function satisfies this input output contract and things like this. But if you want to to prove like global properties of your code, like for example that the state invariant is always preserved and things like this, you do have to design with verification in mind. And that becomes challenging as well when we see some of the tools that we've developed like LemmaScript, which try to really cater to TypeScript code bases. And also one thing we found with Daphne at least is that given if we have a verification fit, so if we have a code base that fits our patterns of verification, we haven't found that proving it by itself is the bottleneck. So for example, I had some benchmark yesterday where I removed all the proofs in one of the dafny-replay code bases. So I did it once by removing all the proofs but keeping the lemma decomposition, and once removing all the proofs and not keeping the lemma decomposition, so only keeping the theorems if you want the final things we were interested in proving. And in both cases, Claude Code can just run on like an automated loop, and it can do the proofs between 40 to 1 hour, 20 minutes. So it's not trivial. It takes a lot of time, but it's able to do this because it kind of takes the problem step by step. It creates its own lemmas if needed. It leaves this as axioms and proves the rest, and then comes back. So it's really is is um, is working in a way that like suits a pretty modular approach where you kind of have a lemma decomposition, and then you have each lemma can be proved more or less independently. And so by following this pattern, it just grunges through it and is able to do it. And I think functional programming is a good starting point to add verification at top. So we will see in the example that we have with for verifying logic in web apps, that we started with this pattern of like having pure functional code for each state transition, so going from one state to another via an action, and then having a state invariant, and that fits pretty nicely with a functional programming mindset, and then putting verification at top. Now, in terms of actually adopting functional programming to the max and then doing verified functional programming on top of that, there's a lot of like questions of taming of effects that have to happen. So for example, I was looking at let me see if I can bring it up, this open code code base, and it's using a lot of um, let's see, so packages. So this is kind of a Claude Code clone, and it's using a lot of let me see if I can find something. Okay, agent. Yeah, so it's using a lot of these um, well, it's
Is
using
this
a
a
lot of these
permission system?
yeah, this is a permission system, but it's using a lot of the functional programming patterns. So
Oh,
like effect untrace. I don't know if this particular one is a good example,
mhm.
but it's using kind of these effects promise and all that. So it is kind of a very functional code base, but it's very idiomatic using yeah, so it's using yield and effect and things like this and generate object. And because of that, because it's sort of very idiomatic, like in order to verify such a code base, like retrofit verification would be quite tricky, but in principle, it has the right spirit to support verification because it's encapsulating everything into these very clear effect boundaries, right? So that's something that I'm thinking of, like how can we support verified functional programming, where functional programming is taken to the max in some of these cases. And as an example of something that I did with LemmaScript on this smaller code base, so this is a code like this is a snippet from their code base, and basically annotating it with some ensures clause that ensures that there is no so maybe it's not super straightforward to read, but it's saying something that if the parent agent has some deny action and the permission is edited, still we will have the same permission in the result file. Like we won't get rid of a deny action and things like that. So it's just like you can do things like this at this level, and this is kind of like using a functional subset and not really using the effectful stuff, but kind of how do you combine this with the more effectful things, and how do you organize, like in terms of architectural patterns, a code base so that you can have verification of the very important parts of the code base, of the logic, of the state invariants, while also keeping like, I mean, you still have to communicate with the with the um, with the unverified part. Maybe the UI is not verified, but it's calling verified logic as we've done and things like that. Yeah, so this is also an important lesson, and I mean it's well known as well in verification domains, because people really usually do things from scratch when they try to verify them, because it can be orders of magnitude more challenging to verify an old piece of code in place than it is to redesign that piece of code with verification in mind. And so retrofitting verification is even harder at the architectural level when there is like side effects at the boundaries and things like this. And at the end, we do want to prove end-to-end properties, not just like micro-logical properties of some pieces of code, but really something that is satisfied completely by our application, by construction, and we don't need to think about. So the way I think of this is sometimes verification can be seen as a very sharp tool where you prove things that are very specific, and you have a very expressive language for your specification. But if you're doing end-to-end properties like safety, for example, then there are ways that you can be correct by construction, making sure your constructs are always used in the right way so that you get safety for free because you're just using the right approach from the beginning. And I think a lot of the work is also to go from a setting where you are verifying things to then extract useful things that can be done automatically, maybe with a bit of a discipline. So for example, I'm thinking in terms of Rust. Rust has this ownership discipline, which constrains what you can do, but then they can have garbage collection for free with memory safety for free and things like that. Okay, so as I said, I will skip on the part of work at Harvard and come back to this later if we have time or if there is interest. But maybe before I move on, maybe I will pause for a second and discuss these points again. Like, what do you think of these points? Do they seem uncontroversial to you? Do they make sense? So opening it up for people to chime in.
I'll start. I think I agree that yeah, trying to verify existing production code is quite challenging. I usually try to pick off small functions that are like fairly functional, as you mentioned, so they don't have much like side effects, because that is just easier to prove things about. Go ahead, Ekin.
I wanted to add that, like, while doing like those old code bases, what I found quite useful is that first doing the property tests, and then after actually setting down the properties, then doing the verification kind of helps. And
Yeah, that makes sense. Yeah.
easy.
Yeah, and I think this is also something with LLMs. I think it is a very reasonable thing to do property tests first with LLMs. It's just when they're developing a code base, they can just iterate faster on this. They don't need to do proofs. They just like randomly check the properties, and then when things go well, actually do full proofs. So I feel this is a very complementary approach. Ilya Sergey actually had, I think he has a paper. Um, Yeah, I think it's this one, the first one actually, that was right. So they discussed that they basically found that it's very effective to do property-based testing before any code is synthesized, and then basically have the synthesis task guided by the property-based testing, and then do proofs if needed. And in their case, they're using Lean to do this, and they're using their Loom and also Velvet tools that I've also used in LemmaScript. And so within Lean, they can also use this library. I think it's called Plausible to do the property-based test in the same framework. So that's pretty compelling as well. Yeah.
I think there are also tools like, I'm not sure how to pronounce Aeneas, maybe, that
Yeah.
translates Rust code to Lean, and then somehow you can, please tell me if I'm out of the context here, but the proofs that I can do with Lean and the proofs that I can do with the SMT-based stuff, like how much overlap is there, and how much disjunctness is there?
So in general, I mean, Lean is pretty meta-programmable. So what they've done in this system, the multimodal verifier, is that they've actually basically whatever they can discharge a proof obligation to an SMT solver. And the nice part of splitting it this way is that at the end of the day, if you have some proof obligations that are not discharged, you can then manually do them. So you get a manual, like you automatically get verification of your proof obligation, which is really nice. It's something you don't get with Daphne. With Daphne, you don't really know exactly. I mean, you get the VC conditions and all that, but within Daphne itself, you don't have the meta programming to know what is the current state that needs to be proved. In Daphne, what you end up doing is that you can interactively, actually, let me see if I can.
I most of the time let it compile and see all the messages and then read to like one by one.
Yeah, exactly. And this is actually like, let me see if I can. Yeah, so yeah, so in Daphne, like, yeah, I guess you're all familiar with it, but like one thing to think about is if you have let's see, if you have a buggy proof here, for example, this one doesn't work because it's buggy. I mean, you don't really know exactly what is happening here, but you can maybe do a proof sketch. So like Daphne generate sketch, induction, and you get this induction and you see, oh, okay, the add case is actually the one that is broken. So you can kind of drill in by manually adding context in your proof body. You can drill into where the problem is and maybe actually debug it more precisely. But the thing is, like in Lean, that is, and in Rocked, one advantage is that you do get this context automatically generated for you. And there are trade-offs here because in some sense, what is nice with Daphne is that you look at the error message. Let me see if you look at the error message and you see, okay, this is where the problem is. I can drill in, find what the issue is, but and this is actually this auto-active part in some sense, the verifier is active and you're also active doing it. But in Lean and Rock, you kind of often end up going down rabbit holes because you have this context telling you what you need to do at each step, and you end up kind of in a corner that is just not right, but it's kind of hard to take the leap out of it and things like this. But it's kind of a so I think what the work that Ilya is doing with this multimodal verifier Loom is interesting because it really bridges the gap between having the SMT solver but also having the contextual approach from Lean and the meta programming approach from Lean. Yeah.
Thank you.
Quick aside, what was that command that you had in VSCode that like completed the proof for you?
Yeah,
Is that a custom plugin?
That's a custom plugin. That's part of Daphne Sketcher, which is part of the work, some of the work we've done at Harvard. And yeah, so it has this kind of custom plugins, and the goal was really to kind of combine it with LLMs as well and all that. But we did find in our results that LLMs don't really need so much to have the scaffolding of induction done for them. At least there was kind of this. Yeah, let me just maybe go through this example here. So this is kind of the setup where we have these sketchers. So you saw an example of a sketcher, and then the scaffolding paradox is that basically weak LLMs couldn't leverage the scaffold yet, and strong LLMs didn't need the scaffold. So we were in a spot where this wasn't super useful for LLMs, but it turns out to be quite useful for humans. I like having it when I'm coding in Daphne just to see what the canonical inductive sketch looks like, and there's ways to tune what the inductive target is and things like this. So that works pretty well for me.
Awesome.
One thing I also want to ask, do you care about whether your proofs are long and unnecessary steps, or is it just irrelevant as long as
So
it's...
I mean, I don't really care. I think I do care a lot about whether the statements, like whether the specifications are very clear. That's very important. But the proofs themselves, I feel like they're completely checked. There's nothing, like, I don't need to read them really. I don't need to read the proofs to understand what's going on. I just need to read the statement. So I personally don't care too much. I don't know, do people care here about whether the proofs are readable?
I kind of do, because I feel like, imagine this was running on a Pentium 4 computer with this infamous bug, then you know what I mean? I don't know the hardware is really correct. So
Yeah.
I think it should be possible for humans to understand the proof, so, or at least follow through.
Yeah, I mean, I think even in pre-LLM days when I did proofs in Rock, for example, I did find that tactic-based proofs are kind of not super readable, and what you end up doing is just relying on your lemma decomposition for readability. So what you care about maybe is how you've decomposed these problems into these lemmas, and if these lemmas all make sense to you and how they fit together, but you don't care about the detailed proofs. Like it's just kind of too much to care about. And I think Daphne proofs in some ways are more readable because they just look like code, and they have all the steps that are easy, just automatically done for you. But I feel like, okay, at this point, I'm going to trust the verifier. So I'm making that leap. But it's true that there's one place where verified programming is different from mathematical proofs, is that with verified programming, you actually need to make sure that your code is also efficient, right? And that might be, so that means like actually still reading the functional part of the code, the algorithmic part of the code, and the proofs are not going to help in that respect in any case, even if they were readable. So yeah, so I think what you're pointing out is that depending on your trust surface, you might want to be more or less readable. I think it's also satisfying to be readable in terms of insights that you might gain from the proof, but maybe some of these insights can be gained from a lemma decomposition as well.
Thank you.
Yeah. Yeah, but I think in terms of bringing like formal verification to mainstream, I think at this point we don't want to care about the readability of the proofs. We will just like trust the verifier for that. And the question of whether we even care about the formal specification versus a very tightly integrated natural language counterpart to it, that's also a question that is open. Depending on who's using the tool, they might not even want to look at formal specs. But that's a bit of a more radical position. Okay, so the projects I'll talk about today, and I guess you've seen some glimpse of them already, is dafny-replay, which was our kind of like a case study driven way of looking at how to verify web apps with verified state transitions and state invariant. And then lemmafit, which is really a way to streamline the methodology of dafny-replay into a usable package that works with Claude Code to just do a web app end-to-end. And then LemmaScript, which is this way of verifying TypeScript directly. And the motivation is that instead of starting with Dafny and basically incorporating Dafny into the compilation pipeline and having compiled Dafny as JavaScript in your web app at the end, you kind of start with an existing uh, uh, tool chain for TypeScript, and then you have this parallel tool chain which is only doing the verification, and that has the advantage that it's more easy. It's easier to do greenfield and brownfield, though with the caveat that brownfield is actually really hard to verify in the wild. But we'll come back to this. But these are the three projects that are ongoing, and we have more projects in the pipeline, more like kind of follow-ups to lemmafit that are maybe less integrated with Claude Code and maybe also using the cloud a little bit more and things, but we'll see where we go with that. But these are the projects we have today at Midspiral. So in terms of goals for all these projects, we want to verify practical, real applications, and we want verification to guide the development towards a high-quality artifact. So it's not just sort of like putting verification at the end, but really having a feedback loop where the verification is improving the code as it's being generated. And we want the process to be streamlined enough to be accessible to mainstream developers and even non-developers. So think of someone that wants to do a little web app, like a web app, like as a product for something, and doesn't necessarily want to look at code at all, either in Dafny or in TypeScript. So in terms of frictions, well, one issue that we already discussed is that many things do not naturally fall under verification. So for example, UI, effects, and things like this. And the integration between verified code and the rest of the app can be fragile. And LemmaScript in particular, which is really trying to kind of take TypeScript and make a verification toolchain out of it, really has a never-ending mandate to support yet more TypeScript. It's going to be hard to really support everything, and at some point we will have to strategically decide what is the subset we want to really support, or have an extensible system so that any case study can support whatever features it needs into the, like, in addition to the core and things like this. And there's always these gaps that should be kept in mind. So the gap between what we verify and what we want to verify, and the gap between informal intent and formal specifications. And this is the second gap is particularly important if someone is trying to provide a natural language solution to this problem of generating a web app from natural language specifications. So if the formal specifications remain unseen, there's always this gap that really needs to be bridged carefully, and the guarantees should be set appropriately. And yeah, so in terms of how we realize this vision, so yeah, again, it's kind of tricky with this if verification is not thought of from the start, it's kind of really tricky to retrofit. And one thing that I think is going to be really important is to explore and solidify verification patterns, especially how they combine with unverified code. In some sense, it seems like a pity if you end up focusing too much just on the part that can be verified because they can be verified, not because they're important to the integrity of your application. So like really kind of balancing the balancing act between what you can verify and what you really want to verify, and how to integrate with existing ecosystems, and how to work at a higher level than code. So like trying to look at natural language or other things, or maybe like spec-driven development and things like that. So in terms of what we looked at write in Dafny or verify TypeScript. And so the write in Dafny is the dafny-replay model, or the lemmafit model internally would be writing in Dafny. So then the nice advantage of this is that actually Dafny has first-class JavaScript compilation, so it can work pretty well with web apps. And of course, we can use the full verification features of Daphne. And LLMs actually generate Daphne proofs quite well, but on the drawback, there's like a slow and bloat in terms of the compiled code, and it can be hard to integrate with JS despite the JS backend of Daphne. And this is especially true if you kind of have an existing app and you're trying to retrofit some verification and extract some Daphne component and then try to wire it back into your app, you'll get a lot of slowdowns if you do that. And that has been a pretty bad experience for us, which is why we were motivated to do LemmaScript for exactly that use case. So it's native TypeScript, no compilation gap, and then you separately have a verified mechanized model, and basically you do have a verification gap, but it's a systematic translation. It's not an LLM based translation. The LLM just helps with the actual proofs and the actual lemmas you want to prove and things like that. So maybe just to give a sense of how these things look, I'll show some examples. So maybe an example in LemmaScript first. So this is code that already existed in Hono, which is a web app framework supported by Cloudflare. And this is a code that I was motivated to check because it was based on a CVE. Yes. So there was a security issue that basically there were some cookie names that could escape their scope somehow by someone injecting Unicode characters. And then in order to fix that, they actually wrote a pretty simple trim cookie white space that would only trim actual space characters and tab characters and not any of the Unicodes that are treated as white space by TypeScript or by JavaScript. So this is a pretty low level kind of imperative code that you could easily think of it as it's actually only ends here. So some while loops, some return statements. And then with these annotations, we can actually prove these ensures clauses that really says that basically the first character of the result is not a white space or a tab, and and the last character of the result is not a white space and a tag, and then the actual thing that is left is really a slice that is in between those let me actually put the word wrap. Yeah, it's a slice between things that are white space and tabs. So it's a very complete specification of this code. Maybe it's kind of overkill. The code is not too complicated, but at least you know logically that your code is doing exactly what you want. And in some sense, in the future, you could imagine if you have a CVE like this, you don't just have test cases that show that you're fixing the issue. You also have some verification annotation that tells you, okay, I've really fixed this issue. So I thought this example was fairly compelling because it just worked. But the caveat is that the code is fairly low level and simple, very, very suitable for whole logic kind of verification. So this is an example of LemmaScript. And for an example of TypeScript, maybe of lemmafit, maybe before I show lemmafit, I'll just show some dafny-replay. So for example, we could do...
So those are not comments. Those are actually the ensures and verifies.
Yeah, so they're comments to the TypeScript and they're verification annotation to the toolchain, to the LemmaScript toolchain. And this is actually a fairly standard thing to do. So Pharmacy is a verification toolchain for C. And I don't know if I can show some let me see if maybe, and you can see that it uses let's see, it has some example. Okay. Actually, I think there's a GitHub ACL by. Yeah, so there's so this okay here. So standard algorithms. So let's say binary search.
Probably on the header.
Oh, okay. Yeah, so you can see it's fairly similar. It has these adds annotation, and you can see that it has requires clause and ensures clause. So I was kind of inspired by this because I had used Pharmacy in a previous project, which was about like doing stage verification. So staging from like a multi-stage programming setup in Scala to actual code in Pharmacy and doing things like a verified HTTP parser that is memory safe and things like that. So I had prior experience with this, and I guess you could argue there's also other languages that adopt this approach of integrating with the host and kind of being invisible to the host. So maybe another one is Verus. So Verus,
Various
in
with
some
its own
sense,
syntax.
Verus is not, yeah, it's not comments, but it's kind of with macros, the thing appears invisible to the Rust, and then Verus does all this verification on top, right? So yeah.
I've been trying to use that at work with very
Yeah.
little success so far.
With
I
little
figured out.
success? Okay. Yeah.
Yeah, I figured out all the stuff that almost all the stuff that I was trying to do. I can also do it using Datalog, and I found like this Datalog macro that you can call ascent, and I just went with it, and yeah.
Oh, interesting. Okay. That's a very interesting remark. So it was just easier to kind of use a domain specific data log embedding for what you were trying to do than to use the full scale
Yeah,
various.
like
Yeah.
I still try to use the various for the stuff like actually proving mathematical properties, but that was actually little used to us. It was more interesting to do the tree properties of the like we were basically doing tree transformations, and the data log seemed actually like a no-brainer.
Yeah.
And
And that's actually an interesting point in general, like kind of, I mean, in this case, I imagine you were encoding your properties, like you were kind of like encoding exhaustively your properties into the data log, right? In some ways.
exactly,
Yeah.
and like I can just like inject in during the runtime some stuff, but yeah.
Yeah, cool. And this is also one thing that I think might be a solution to the problem of like of LemmaScript trying to do like how could LemmaScript ever capture all of TypeScript and all of the idioms of TypeScript? And one issue is also that like TypeScript, the semantics of TypeScript is not very amenable to verification in the first place. But the other is just there's just a lot of things, and in general, you can imagine having domain specific like things. So let me see if I have in my case studies. Um, yeah, so I think I tried to do this Hono thing again. So let me see if I can find it. And it's in the middleware. Yeah. Yeah, so this is kind of a pattern that I've just started playing with very recently, actually, but like kind of thinking of like, okay, you maybe don't want to formally verify what this call is doing, but you still want to verify something about the function. So you kind of do a havoc, meaning you can think of file name being assigned to anything, and then you do this unsound thing, which is to assume something about the result. So this is part of your trusted base. What you're doing, you're assuming that the file name, the try decode URI is matching this decoded a function that is written on the Daphne side. So it's a ghost function, which in this case doesn't really have much semantics, just that it's a deterministic function, and you can kind of encode it like that. So, and then the proofs has these axioms in them, but they're very clear what they are, and you can still prove something about the result. So kind of thinking of this pattern further, imagine if here you had some sort of regular expression, you could imagine having this kind of pattern of assume so that the Daphne verifier wouldn't really be dealing with regular expressions, but there could be another engine that actually makes sure the regular expression matches the behavior that you want more precisely. So kind of basically it would be like a way of extending things where some some things are havoked and assumed, but then another tool could actually go there and make sure this havoc and this assume is justified in some sense. So yeah.
Can you
So
just real quick just define what the havoc operator does?
yeah, so the havoc operator, if you look at the Daphne code, what it does is that it says file name can non-deterministically be anything, like any string. So that's a feature of Daphne that you can do that you can say this is like it's basically not specified what it is. But then by using this axiom, you kind of make sure that it has the shape of what you care to do. And basically this example is really just an example of composition. So you're composing these two things that you don't know very well, but you can still prove something about the composition together. So like if you had mixed the order of this composition, you wouldn't be able to prove these things. And that is actually motivated by a real bug, by some real CVEs that where the order of these things was messed up, and so it didn't work very well. So I don't know. So for this particular feature, I don't have the lean counterpart. I assume lean would have something like this as well to do or it would be something you could add to Loom Velvet. It wouldn't be too hard. It's really just think of it as like everything you knew about. I mean, in this case, basically this means you know nothing about file name at that point, and then you kind of do more things with it.
Wouldn't that be basically an existential existential type in the lean kind of deal, like dependent sum or something like that? Because there exists a file name. Isn't that what
Yeah,
we're
but
doing here?
yeah, I don't know. I think it's a little bit more subtle than there exists a file name um, because you don't actually like usually when there exists something, you're saying it's deterministically there is one possibility and you know what it is. But here you don't actually know what it is at all. It's really just like saying that um, your system is completely like removing anything it knows about file name, but then this is kind of restoring it. So maybe if you take these two things together, you're right that if you take these two things together, it looks like you're saying there exists a file name such that this property hold of the file name.
And then
So
I
in
can
that
say
sense,
just sorry, and then everything is okay, like, right? Like as a proof of that statement in the lean version.
yeah, so you can say you can have an assertion where the proof is sorry and you would get similar effect, I think. Yeah. So these are not great as a first measure. And I think one thing is also if you're using LLMs and you're kind of sanctioning the use of these axioms, then it might just use them as an escape hash, and now you can't really just see if they're there or not, because some of the uses are what you care to have and some are not. So I was just experimenting with this a little bit. I think it's slightly less meaningful, but I did want to do it because I was trying to see how can I prove something in a bigger code base and not have to prove every single part of the bigger code base I use. Like, I mean, in general, this cookie example worked really well because it was a self-contained method and everything kind of made sense. This method here makes sense. It's just a primitive operation that you have in TypeScript to get the character code at something. But once you start mixing, like crossing boundaries, like how do you actually make sense of that? And that was one way to think about it.
One more question about
yeah.
your example. When you go back to the index, you had that decoded function, which in your index.ts, I didn't see it defined. I see in the Daphne file, it's a ghost function. I was curious because when I was trying out LemmaScript, I wasn't sure how to create a ghost function in the Daph or in the TypeScript side. Is it just that it's undefined and therefore it automatically creates a ghost?
That's a good question. So we can see if it's defined in the, so it's not defined here. So the user just decided, I mean, the LLM just decided to define them as ghost functions here. I could have defined them however I want. I can in general have, I mean, that also answers one of your questions about, in general, like the way it works for the Daphne embedding of LemmaScript is that basically from the TypeScript file, because there's an add verify annotation here, this particular one is going to generate like this method here, and it's a gen file, it's incomplete, and also it's generated this because options are kind of used when you have like a return type that is possibly undefined, you get an option type instead. And actually part of the difficulty of the LemmaScript compiler is to deal with all this flow-sensitive narrowing that TypeScript does with undefined in unions and things like that. So anyway, so you have this, and now this file has to be a strict superset of the gen file. So you see that it added these two lines, and it might have, and I think that's the only thing it added. So it had to specify what was the meaning of these predicates that were not these predicates, these functions that were used. And it could have decided to actually implement them if it made sense. But in this case, it kind of made more sense to just leave them abstract because that's kind of the only thing we are using from these functions is their deterministic existence in some ways. So the fact that we're using the coded row path here means we can use it in the conclusion here and have these things match up in some sense.
Nice.
Yeah. And also coming back to one of the questions you had about LemmaScript. So does LemmaScript support Lemma? And actually, both in the Daphne and in the lean embedding, what you do is if you wanted a lemma, you would just add it to this file. So it doesn't need to be supported in the TypeScript itself. It's supported in the backend generated files, like augmented.
Cool.
Just to be clear, the GAN file is generated deterministically, and the index file is created with an LLM. Or did I
Yeah,
get
so yeah, exactly. Yeah. And of course this could be, I mean, this could be done manually too, but yeah, the point is that this requires some creativity, like not in this particular case, but in other cases, like let me see. So if I do a bigger example, so like this is a game of equality. So this file is fairly simple, and this is a function reachable that doesn't even have the whole specification here. It just has some bribes of it, but it's a fairly tight algorithm. And then you have can equalize and things. So this is a fairly simple equality domain, but then the equality DFI is actually super long because it's proving
proving ring, right?
it's proving what, sorry?
Ring, like it's almost like
It's proving like soundness and completeness of the decision procedure.
Which domain is it? Is it like the rings or groups or like?
Ah, okay, yeah. So the domain is like you have some. So let me show you. You have so you have some cards, and you kind of okay. So I don't think I can do this one. So you have to make these two sides equal.
Okay.
And I think yeah, and basically, yeah, you just can use these operations here, and you can use division if it's wholesome and things like that. Yeah.
Okay.
So in this particular example, what happened was that the TypeScript one was actually quite elegant because it was fairly low level, but it was a nice kind of algorithm to do the almost like a nice algorithm to do this. I also have it in the lemmafit version, which generated a domain that has all the proofs as well in it. It's maybe harder to see what's going on because the proofs are there, but the domain is also pretty simple. You can see in in Daphne, you have like these different operations for an expression. You have the game mode, you have the action, deal more, submit claim, new round in a deck. You have the evaluation function. So this was all LLM generated from a small letter and a language description of things. And then it kind of like it kind of ended up like doing a lot of things for just proving the complete and everything. So this is also doing the state invariant, and now it's doing the soundness claims and things like that. So anyway, so there's a bit of a difference between these two things, but both of these games were done separately, like just one using LemmaScript and one using lemmafit, and they kind of both worked. I mean, I would say like doing Daphne first kind of forces thinking about verification first, and then doing TypeScript first kind of you think about the low level algorithm first and then kind of think, okay, how do I verify this? But then there is a back and forth. So these things kind of equalize a little bit. And yeah, I mean, I have other examples. So one example that I have in the test cases that actually I can also show some lean code for. In LemmaScript. So it's this, so we have a few examples, but this is this topological sort example. And this was actually extracted from some real code that an LLM had written in a different project. And maybe this is simplified a little bit using maps and sets and all that. But you can see there's a lot of invariance here. And this is actually a little disappointing in some ways because it's not proving much at all about the result. It's only proving that basically the topological sort hasn't changed the length of the array.
Also, it doesn't say anything about this comes before then this, and
It doesn't, yeah, and it's still already pretty complicated, and it's doing a lot of invariance. And actually, this is one example where the Daphne kind of worked pretty straightforwardly. I mean, it had to define. You can see in the code that it had to define some helpers, and it's eventually just like does this part like this. But the lean one took forever, and it was pretty complicated. Like it took a long time for this to go through, and maybe this one is a little pathological because it's an example. Okay, now it's starting the lean server here. I'm not sure how what this would do, um, but it's a pretty long one to verify, and it almost felt like very not within reach. Like it took. I was letting it run by itself, but it took like many attempts and many false starts, and it was really getting lost into the details of how to do this. And part of it is the complication of using Loom and Velvet compared to using Lean. Like you have these names that you have to strip, and you have to kind of know exactly how to put these things together, where to use the helper functions and things like this. So there was a bit of complication, but that was one example. And then the thing is that I wanted to actually do this in place, and this was in a code base where I was using Daphne. So this is the bigger setup where I'm using this workflow, and part of this workflow is that I need a topological sort, and the topological sort is defined here. So it's actually fairly similar to the one we've seen. It's proving a little bit more because what I did in this example is when I throw an error, actually the code, and maybe that's a bit too strict, thinks of it as an assert false. So the system has to prove that this code is actually unreachable. And that took a long time. And then the Daphne code was fairly complicated and fairly advanced because it used a lot of like opaque, yeah, so it's not verifying within the timeline of the IDE, but it used a lot of like opaqueness, unrevealing stuff. So pretty advanced feature that it had to figure out for itself, like these are opaques and things like this to tame the verifier. So this is an example that kind of a cautionary tale that like something that looks simple and we haven't even proved the interesting part yet is kind of complicated to do, you know, both in Daphne and in Lean, but especially in Lean, it was almost like not within reach. And yeah, let me see if I have, I think these were some of the, so in terms of, yeah, let's maybe go back to the slides. Are there any questions before we go back?
I just have a little remark. In my humble little experience, LLMs were way more successful using Daphne than Lean. Somehow
Yeah.
they always get confused between Lean 3 and Lean 4. And even when they got it right, they just kept hallucinating for some reason. But I don't really know why.
Yeah. So I think the auto-active part of Daphne Hub, so this was, let me just show you some of the stuff we've done at Harvard, which was early on, we did this synthesizing multi-step programs using a verifier, a large language model, and tree search. And the setup is that we used programming languages that support formal verification like Daphne, Rock, or Lean. And at that point, this was in 2024, yeah, Lean was like, LLMs were completely confused about Lean 3 versus Lean 4. I think it's much better now, like they now have moved on to Lean 4. But yeah, so we consider the problem of taking an English language prompt and generating all of the following: specifications, code, proof of correctness. And so one example might be like this. So this is similar to the code I showed earlier in Daphne with the Daphne sketcher. Basically, you have, this is the prompt. You ask it to write a data type for arithmetic expressions, write an evaluator, write an optimizer, then prove that the optimizer preserves the semantics, then prove that the optimizer is optimal with respect to the specified criteria of optimality. And if you have something like that, then in Daphne, you can really just state lemma optimizer preserves semantics, and these are universally quantified. So you're proving it for any expression E and any environment. You're proving that the optimized evaluation is the same as the unoptimized evaluation. And this is actually something that, depending on how you've defined your functions, Daphne usually prove this automatically. So that's a great boon. You know that you're on the right track if you got it. And so we were doing a Monte Carlo tree search, but I don't necessarily have to go through this. So it's kind of, I always find this part interesting when you're doing, I think maybe it's just kind of an interesting a thing to think about when you're trying to do this search step by step for something. So here we were doing, like, the root program was basically, think of it as just the prompt. And then here you had a partial program, like a step-by-step partial program, just even left to right completion program. And you're kind of extending it with more completion step by step. The LLM is doing the completion part. The verifier is evaluating and maybe expanding, and then you have this back propagation. So this, nowadays, this might feel a bit low level. It was kind of like maybe trying to get a handle of how to interleave these things more than is necessary now with agentic coding. But what is interesting is like if you think about the algorithm to kind of select the next node to look at, so what are you doing? You want to have this trade-off between exploration and exploitation. And it's kind of just an interesting scalar formula to get there. So you're kind of taking the average verifier feedback, this kind of constant that is about controlling how adventurous the search is, trying to do progressive widening, and trying to really favor underexplored actions. So if you're looking at all the actions, all the number of things coming from as a particular step, you're kind of favoring actions that are less explored. And really, this is kind of balancing exploiting the verifier feedback, the positive feedback, and exploring underexplored action. And it's all just in a scalar. So I find it kind of interesting how these formulas just come about as these things that are really just summing different things up to do this trade-off. And then what we found in that, so in our system, what we were doing was that we were considering fader states, not even adding the node to the tree for a fader. And in case of incomplete state, we were actually adding it optimistically. And if we had a complete program that satisfied all the parameters, we would return success. So this is where the verifier feedback came in during expansion. And what we find in our system was that here I'm using Rock, but I would say Lean wasn't even in the picture then because of this confusion between Lean 3 and Lean 4, but we had some preliminary Lean results as well. But I think the reason Daphne was so much better, like just comparing how high this bar is compared to this one, is because of the semi-automation and the fact that for many cases, the proofs just work. And also like this idea that in Daphne, you kind of have success is implicit. Like if things are just going to work trivially, you don't have to say anything. But in Rock or in Lean, if you're doing a case analysis, you still have to kind of specify all the cases or like automate the specification of all the cases. Like success has to be defined explicitly as well. But in Daphne, only failure is explicit, which really simplifies things. Yeah, so any more questions about this? Yeah.
I also think like the Daphne syntax is kind of helpful to the LLMs in a sense that there are less functional programming languages out there compared to, the, yeah.
Yeah, I think that's true. I think one thing that comes across really nicely in Daphne is that, well, this example is wrong because the proof doesn't work, but let me show you here. Yeah, so in this example, I mean, it's similar, but this actually works. What's interesting is that induction, so we're doing a proof by induction. It's kind of surprising that this is necessary, right? That like you would think Daphne could automatically do this part, but anyways, like the proof is by induction. So in the add case, you have the inductive hypothesis for the two sub-expressions. And basically, yeah, so the nice thing is that induction looks like recursion, right? It's really just, you're just writing a recursive program, and it's actually an inductive proof. And I think even just pedagogically, that is a very useful feature. And of course, that means that this has to be well-foundedness, otherwise your function wouldn't be terminating, right? So if I did something like this, then cannot prove termination, right? So there's a pretty clear like notion of well-founded induction related to well-founded recursion.
I still try to figure out the opposite version.
Hmm?
Apparently you can also do like the code data stuff in Daphne, but I couldn't manage it so far. I tried to encode the classic Haskell thing, having like this infinite formal power series and multiplying them and stuff. But I wasn't able to encode it yet.
I guess we could do. I mean, let me do. Like, I think you can do code data type. Yeah, okay, so it's already completing that for me. So you can have like this. So this is a code data type because if you defined it as a data type, you would not be able to show that this is well-founded,
There
right?
is no
In base case.
basis.
Yeah,
Yeah.
so it's a code data type. And now I guess it wants to, yeah, so now, yeah, so this is a mistake of, so now we have something like this. Is it just not doing the right thing? I don't know what this autocomplete was doing, but
I think you want it to be a function, not a method. The function method was the syntax from long
okay,
ago.
yeah,
Yep.
yeah, okay. Yeah, so a function like this, thanks for studying. So yeah, so anyway, so yeah, I was just playing with the autocomplete. I don't know what it is, but basically this is well founded because every time when we're matching against the stream, we are destructing it in some ways, and we're doing something like that with it. So I could also do, I
Yeah,
suppose it
but
would be more,
I guess we
yeah,
always produce something, right? That is the
yeah, exactly. You always produce something, but maybe I could also do a map, right? And would this be well founded? So I mean,
I,
map
I,
is actually taken.
I
Let's see
found that there is like this weird flag. I don't. It's very little documented. When you edit, it becomes okay. It's. I think. Wait. Let me check. We kind of experimented with.
No, so this works, right? So this I can define a, like I can basically consume a stream and generate another stream, and as long as I'm consuming, as long as I'm not like the thing that is not allowed is to basically use it directly, right? So here, for example, okay, so I can do this, but I can't do, I mean, that would be intuitively, that makes sense that like if I did something like bad and I just didn't produce anything, that would be a problem, right? So like that wouldn't be allowed, cannot prove termination because you're not producing something at every time you're going through the function. Does this make sense, or is there a better way to say it?
I think it makes sense.
Okay. Yeah. So I think
You should
I think
also be
again
able to
it's kind of, yeah, go ahead.
yeah, no, on line 5, the little 3 dots under the from, I think should say that it's a co-call. I think a co-recursive call.
Okay, how do I actually,
They usually just
I
highlight.
I might not have, yeah, I think I think I generally don't have highlighting in VS Code because it's very distracting. So
I see.
I guess it
Okay,
would be
yeah.
useful here, but yeah, okay, cool.
So if we go back to the slides, I think there were some questions that I sent you beforehand. I think maybe those might be good to sort of finish
sure.
up, and then we can sort of get to questions
Okay, sounds good.
or other.
So let me see if I didn't get too far into my slides here, but
We can come back next time if you'd like.
yeah, we can come back. Yeah, okay. So let's maybe go to your questions. So these were questions that you seeded. Happy to take other questions. So we saw that actually for multi-set support, I have an example where the multi-set support is exclusively in the Daphne part, and the TypeScript doesn't need the multi-set support, but there might be a question of especially if you're targeting both backends, if you want to specify multi-set properties at the level of the TypeScript, and also if you were trying to integrate a multi-set library from TypeScript and like map it directly to say Daphne multi-sets or things like that. And then
I mean, I guess my point here would be like, because I'm imagining I'm starting a project in LemmaScript. I want to have my code as well described as I could in the TypeScript, so that way I know exactly what it's doing, and then the AI could try to generate as much of that other stuff as possible based on the TypeScript, because that's where we're starting, right? Is that we start with the TypeScript, annotate it, and then it generates the Daphne
Yeah.
code. But
Yeah, I think that makes sense. It's also not something I've been respecting like religiously. I think especially if you're
okay.
using both backends, you want to centralize everything in the TypeScript, but you can assume that you could also look at the Daphne file to see exactly what was proved or things like this. And so I think that's a question of like, if I have the choice between adding a feature in the TypeScript versus like just it's already available in Daphne, I can just use it in Daphne. Sometimes the trade-off is not super clear. Yeah.
I see. That makes sense. Very practical.
Yeah. And also for lemmas, it would be kind of like I guess lemmas are not that hard in some ways. They're just like they're not different from function contracts, right? Like in what they would be doing. So they would be I could imagine a path towards specifying the lemmas in TypeScript, but right now they're completely in the Daphne or in the lean part. Yeah, and also the reason is that initially when I was doing the lean version, so lean has a nice feature that you can have the code in a separate file from the definition. So I was pretty religious about separating definitions which would be generated from proofs that would be like in a separate file that would be completely under lean control. And so that was the conventions that I used with lemmas. But yeah, again, it's kind of I mean there would be other ways to do it as well. But since lemmas often require proofs, it might just be easier to fiddle with on the backend side, on the verification backend side.
Cool.
Okay, so to support brownfield development, have you considered external definition files? Seems like it required a new version of definitely typed. Yeah, yeah. So I think having files that annotate
Sort of explicit function preconditions
yeah,
and postconditions.
yeah. I think that would make sense. That would be a nice way to consume libraries. Right now, I have a way of I've started playing with these things very recently, like even just yesterday, like after this question of like basically I think there was an example of this in the um, I can so I have a way of like getting an extern function, for example. So you kind of can get the signature of something from within the library context of TypeScript. So you can do that, and you can also define what is the external signature for something. But I think having a file which specifies like exactly what is the signature of a library, that makes a lot of sense. I think it would make things more modular in some ways. So that would be nice.
You could even have like first class modules as in
Yeah. So I think that's a good idea in general to support extensive development. I haven't tried to do too much like cross-file verification. Each verification is just one file, and then if you want to verify another file, you just verify it. But then you can already cross-import the signatures with the ensures clause from one file to another. And they become, let me see if I can wait, where is the wait, how do I search?
On the left, there's the little search icon. Just,
Where is it? Oh yeah, right.
straight left. Straight left.
Yeah, so yeah, so these were okay, so here was one example. So it would generate this axiom for string splitting, for example, but that was done at the library level. That it makes sense that you wouldn't necessarily want to specify exactly what goes on, but you can still use it, assuming that it has the signature. So you could imagine if you had an external file, like module declaring all the functions, you can just have them be function axioms in the Dafny code, for example.
Yeah.
And maybe there's ways to, like, if you have multiple things to actually check them at the end, but that would be a separate problem. So I think that's a good idea. Would it support the standard library? Yeah, so I think in general, and for this particular case of LemmaScript, right now the standard library, if you want, the preamble stuff is kind of ad hoc. So the code base is adding these preambles depending on what you're using in your code from the TypeScript side. And that could be a little bit more streamlined and also more extensible. So having a standard way of like saying that you're reusing parts. So I think, yeah, a standard library would also make sense. And I'm not, in terms of whether I'm focusing purely on the web environment, so I'm not. I've also considered server-side environments, and actually some of the case studies that were ported from dafny-replay, like the collab to do case study, is actually using Deno for server-side, for serverless edge functions with Supabase. So that's kind of supported. Like there's nothing too special to do for that in this context. Maybe the difference is which subset of TypeScript is actually available on the front end versus the server side and things like that. So I don't necessarily think of math being a special case. I guess I can see why you say that, because like of how numbers work in JavaScript versus how numbers work in formal verified systems, like no overflows and things like this. So yeah, so that does make sense. It's kind of yeah, a segment on its own. I think it depends what people end up verifying with these things, or like maybe it's a question of qualifying the statement that is being verified. But I think it could be. It sounds like a necessarily hole to plug in some sense, that these numbers are not behaving the same way. I mean, the way Dafny does it now when it compiles from Dafny to JavaScript is that it's using this big number JavaScript library. And I wouldn't have that luxury in the sense that like I would want to go with the TypeScript semantics as they are. But yeah.
Well, I think when I was asking this question, I was specifically talking about sort of the lean mathlib equivalent for Dafny, something that would allow you to quickly build axioms about, or sort of, not axioms, but lemmas about sort of more complicated objects in Dafny. And like, so like, for example, you mentioned there was like already a multi-set class in lean, and then you could also use that to do various reasonable things with like lemmas about multi-sets.
I think there might be a catch though, because like the catch is that math can be, I mean, the fact that mathlib is so standard is also a feature of the lean community, but at the same time math can be standardized in that way. Like people will be like, oh, I just need a library that has axiomatized topology for me and I can just use that or something. But if you're doing verified programming, it seems a little harder. I mean, maybe you can have like some data structures that are like verified data structures or things like this. But it seems like every code base is like starting anew. So the thing I would want to figure out is what are the verification patterns, or what are the core components of verified programming that keep coming up. And maybe in this case, they will all be tied to the idioms of the language being, many things would be tied to the idioms of the language being, like being the initial language, the source language, like TypeScript or something else. So having libraries that support that would be more like a standard library for going from TypeScript to Dafny. That would make sense. Trying to do a lot more might just make it like kind of not quite matching what is going on at this source language. But I don't know, maybe there are ways to deal with that.
I would say it would be very useful to have like a verified data structures kind of deal, because then it will get the 90% of the job done, right? In a sense, no?
Yeah, but then it's like, so you would want to verify it at which level? Like, would you want to verify it? You would have a TypeScript library that has this data structure and that is using LemmaScript to show that this data structure is verified, or would you want to have a verified instruction at the level of Daphne, and then that wouldn't quite fit with the TypeScript stuff that you have, or like, so it depends in what context you're using Daphne. I think in general, having a useful standard library for Daphne makes sense. I'm just wondering, in the case of this particular pipeline, whether any improvements to the library at the Daphne level translates to improvements to the what you can verify in TypeScript.
Interesting questions.
Yeah. And then what do you do if you leave the decidable SMT fragment? Does Daphne have solutions? So I know Rustan wanted to be more careful about the like the notion of arithmetic, like the decidability of linear arithmetic versus like unrestricted arithmetic and things like this. I think in general, like I don't feel when I'm programming in Daphne that I'm like thinking explicitly too much most of the time about the decidable SMT fragment. I'm thinking, is my proof going through? If it's not going through, which asserts do I have to write for it to go through? Which lemmas do I have to write? And so it kind of feels like a more iterative process that is not really based on a mental model of what is decidable or not decidable, like at least in my case. I don't know if others have different experience there.
Kirsten, you want to pop in?
As soon as I found the mic, yeah, I mean, it was not a problem in practice so far with Daphne. I was just wondering if that could become a problem, you know, if you're doing obviously more complicated stuff than I ever tried in Daphne. And yeah.
Yeah, I mean, I think it scales like
My impression is just
seems,
as Daphne is more push button. So you could like with Lean, you could just, you know, hold Lean's hand more and guide along, but you know, maybe I'm just not good enough with Daphne. So, but I was just wondering if, you know, the push button fails, you know, if you then get into difficulty sometimes.
I mean, I think it's I personally find it easier to have, and I think LLMs as well, they like having a big picture is a little easier in Daphne than in Lean. But one thing that is a bit of a problem is because everything is so like all the success is so implicit. Say as you have a data type and you add cases to your data type, and suddenly the complexity of your program has increased, then very suddenly you might have this issue where things that were going through automatically before are not going through automatically before, and now you have to fill in all the cases to see what is happening. And because in Lean and in Rock you pay the price more incrementally for the cases, then as you scale up, it might just be a little easier to add one more case in some sense.
Yeah, I was also wondering, yeah, I mean, I was just wondering, I mean, I'm not an expert in Daphne, but in Lean, I thought you basically have the same thing if you want. I mean, you have a re-implementation of Z3, basically. You could also have like this, so you can use grind, right? And you have also like this automatic steps now for like inductive proofs, so inductive data structure, which makes really quite convenient usually too. So I thought that maybe that Lean should have everything that Daphne has, basically like the SMT solvers, you know, but you also have more in case you need it for some edge cases. So I guess that was a question, if that's something you miss in Daphne, or if you don't miss it in practice, you know.
So I think I miss having a reified context sometimes, but I can regenerate a reified context by actively playing with the with the code as I've shown in the initial Daphne example. I must say that at this very moment, Daphne semi-automation is just working much better than
Interesting. Yeah.
than what
So it's,
Lean can do with SMT solvers and all that. I do
okay,
find
that's interesting. Yeah.
I do find what Ilya's group have been doing with Loom Velvet very compelling. So it's a very compelling sweet spot that they will have the verified context, but at the same time they can discharge to SMT. But in terms of like the case studies that I have, especially something like the topo sort, which actually, I mean, I didn't even get to the interesting part of like proving something with that. Like I have a few examples where the lean just got stuck, and maybe it's maybe my driving of LLMs that isn't as good in lean as in Daphne, but I do have a sense that like Daphne takes care of a lot of like streamlined cases for you, makes it lets you focus on the difficult cases, so it works pretty well. And the problem with not having a verified context is something that becomes important as a development scales up. But again, it's kind of like recoverable somehow. Like you can recover tediously, or using like something like Daphne Sketcher, you can recover what is the context more or less manually around the case, and LLMs can do that as well. They can probe a body, a proof body, and add if statements to see which condition is failing, add assertions and things like this. But it would be nice to have a context, yeah. But the reason why I decided to focus LemmaScript on Daphne at the moment is because it was really just much more effective. Like I could go much further than with the lean examples. With the lean examples, I would get bogged down. But it might just be also the setup that I've used. I'm also using like, I mean, Loom Velvet is great, but it's also like a less used academic project and things like that. So I think I might be hitting some rough cases that in a few years the landscape would look different. But currently, I think Daphne is ahead.
Okay, thank you.
I kind of have a follow-up question on that. So in Lean, we have like this nice meta programming capabilities, right? Like we can write tactics on our own. I kind of missed that in Daphne. Do you plan to add something like that, or is it even feasible to the TypeScript verifier or to Daphne?
To the TypeScript. Yeah, I don't know if that would be the right level at which you could add stuff. Let me think. I mean, I think yeah, I mean, I guess the things I've tried with Daphne metaprogramming was more on the Daphne Sketcher side, kind of making very explicit what the structure is so that it's easier to drill down, and I find that pretty useful. And then on the TypeScript side, yeah, do you have a sense of how the metaprogramming would look like? Like, what would it be like?
Do you think it would be useful, or it would be just like a gimmick that would basically useless?
I think I'd have to think about it. I think there's something that is becoming unwieldy with my approach to LemmaScript, which is that TypeScript is a very huge language with so many different idioms and so many different ways, and I would want to have some support for extensibility. Now, maybe would that involve metaprogramming? Maybe that could be interesting. I'm not really sure what it would look like. I think I still have to build the core first to decide on the metaprogramming later. But I think adding metaprogramming to Daphne itself would be a different question. Again, it goes back down to this question of verification of the context, which is not something that you can easily get from the, like, even if you like, even say if you went into the boogie level and tried to get like the conditions and all that, it wouldn't be in terms of the source and things like that. So that's one drawback. So I'm not really sure. Yeah, at this point, I feel like I have my main concern is to make it like more streamlined with the just supporting more of TypeScript, or even maybe thinking about like, is there a way to open up the source language? I guess that's a direction in which Strata seems to be going, which they want to have this one intermediate language that supports all kinds of source languages like Java, Python, and I guess they're not particularly thinking about TypeScript, but why not? But I think the idea of like opening up a verification toolchain so that the source is extensible seems interesting to me. But yeah, I guess I want to first do a little bit more experiments with what I actually need in the language. I guess the modularity story is important. So I think what has been suggested here with like the external definition files is a good thing to do. And yeah, so I think it's, I mean, I'm generally interested in metaprogramming, and I've wondered how to metaprogram Daphne, like usually thinking of it more as an external tool. And also one thing that comes to mind is that the metaprogramming doesn't need to be perfect because the LLMs can jump in and also like complete things as needed, you know, so it's kind of like a different world for metaprogramming.
There is an interactive proof mode for Daphne that looks like
It's funny.
Bruce and Leno developed. They published that, I guess, in 2025. Yeah.
So Stefan actually was in the chat earlier. He was our last guest speaker, and he presented that system after Popple this year. So yeah, we're familiar with it.
Yeah, it's more fair to say that he has developed it. I've talked to them and advise, I mean, every month, but so I happen to be on the paper. But yeah, that's Stefan's work and his students, which is exciting as well.
Cool. I should check how they like the mechanism for it, because I'm wondering how they like if they managed to get how they managed to get the proof state working.
Yeah, so actually, I mean, you could see it as a prototype in the sense that that they're encoding things in the when going down to Boogie so that they can retrieve some things from the SMT context or from the SMT formulas actually that is going down into the SMT solver, and then and so there's a lot of translation. I think that if one were to do something like this on a full scale, that one would want to build it at a higher level, kind of along the lines that you've been thinking as well, Nana, with like showing more of the verification context at the source level. And I think so the work that Stefan is doing there also, it's the user's point of view. You see things from the in the source language, and I think that's super important. That is, you don't want to see at that point the encoding into Boogie or into SMT. I mean, it gets too complicated. That's not what the programmer's head is. So so that thing is exciting, I think, in his work.
Awesome. Well, anybody else have other questions or projects or any other comments they want to share?
I have a very I have a question, but I'm not sure if it even makes sense. But there's this programming language called Flix, and they're having an effect system using Boolean unification. And I think they're also using an SMT-based system on the compiler. And I was wondering if that would be possible in the Daphne or any of the verification languages, given that they are using. Yeah. So they basically add a Boolean kind to their a Boolean kind, and they also have like and through that Boolean kind they can encode effects. Yeah.
Boolean kind, like, is it
yeah, like
kind of like the Haskell kind system, or
there's like this regular types that we have, and alongside them they also have like this Boolean algebra, and the unification over the Boolean stuff, Boolean domains is apparently like like you can compute it. It's like it's even stronger than decidable. Like anyways, and it's just works nicely. So I wondered if that would be also.
Yeah, I don't know enough at a glance to comment. I mean, they seem to have algebraic effects as well. They seem to have a bunch of things.
They just do this algebraic effects deal through the Boolean stuff. Like
Oh, I
Boolean
see.
unification.
Okay. Well, I'll check it out. I mean, I guess so I think in particular, like my sense is that Daphne has less of an effect story than say F star, for example. F star has this Dijkstra monad, and it's pretty like it's pretty programmable in some ways. So like for example, if I were thinking to translate those functional programming idioms, something I was thinking maybe an F star backend could make sense just for that instead of a Daphne in addition to the Daphne backend. But I don't know. I think it's a question of like, for me now with the TypeScript stuff, it's a question of like what people are doing in TypeScript. And of course, they might not be doing things that are extremely checked anyways, but maybe in a verification and context, they could be checked. And what would we want to check about the effect glue, so to speak, on top of the actual operation? Like I was thinking of like, in some sense, if you erase the effect and you look at the semantics of what is happening within like the update functions of say an effectful monad or something, then already you can kind of reason a lot about what the function is doing, or like reason about the invariance of the effect of the transformation and things like that. And I think that sounds like something I should look into, just understand what is their advantage, like having this Boolean kind and how they encode effects with this. I mean, this code here looks pretty nice, to be fair. Like, I mean, it's just like adding these different handlers and like having this run. So the question for me is like, I think also in terms of the work I'm doing, I'm wondering about like, again, this green field versus brown field. And if we do brown field, we are fairly limited to what people are doing in TypeScript already and what are the kind of TypeScript ecosystem we want to support. But if we do green field, we have much more opening in terms of doing things that are just like correct by construction and like more yeah. So that's one.
Oh, sorry for breaking you up.
Yeah.
I just wanted to point out that they explicitly like strive really hard to do like Java interop, which is super effectful. So that's why I thought it was a bit maybe relevant, because apparently
Yeah,
they
it
can
sounds
use.
cool. I mean, I knew about it, but I didn't know in detail about it. But I'll definitely take a closer look. Yeah. Thanks.
Thank you.
I have another question about so LemmaScript. Obviously, TypeScript supports like type unions, type intersections, and that I can't quite imagine what your approach is going to be for converting that to
Yeah.
Daphne so
Yeah.
far.
Yeah. So I think there's there's two approaches. So the first is now for union with undefined, that is supported with an option monad, and this is treated fairly extensively to make sure that the narrowing is done correctly. Maybe it's a bit kind of overkill that I did all that, but it just seemed really necessary for even any random TypeScript code base, because they will use an if to narrow things down, and that's actually not a bad match with Daphne in general. I should like, Daphne also can kind of figure out the types more precisely by the conditions. But I think so this is for one of these things. Another one of these things is if the cases can be type tagged and not and they don't overlap. So for example, if you have an array or something, that seems to be a case, and that happens often, say if you're doing LLM, like LLM responses, you might have something that is either an array of things or like an array of messages or just one message as a string or something. And so that one you could handle, I guess. And I guess if you wanted to generalize a bit, you could handle cases that are mutually exclusive and that you can have type tags for. You could handle that. And then cases that are actually exclusive, I guess you would just end up, you could fall back to an explicit, in any case, you could fall back to an explicit data type with all the cases as a disjoint sum. So you could do that. I haven't really gone too far that route. I experimented a bit with like special casing arrays, but I wanted to have a better solution in general. Yeah, I mean, I think I don't know, and also in the work that we're doing with like the continuation of lemmafit, we are still going Daphne first instead of like because it's greenfield, we can do that, so we do Daphne first. So I'm a little bit like yeah, I started going down this rabbit hole of TypeScript, and I realize it's a much bigger rabbit hole than than I can
Maybe we'll pass this to Rustin. Like, what would it take to add type unions, like TypeScript type unions in Daphne?
Well, let's see. So first of all, it's open source, so
Yeah,
so
okay.
feel free. So let's
Yeah.
see. So I would say that in my experience, the most difficult part of the Daphne implementation, well, to me, since I've done so much like on the verification side and sort of understand how to encode things there, but the implementation itself, the most difficult part is the type inference. And I redid that a couple of years ago and spent, I mean, like it took me 2 years to complete. So adding something more would be more difficult. Then again, if there are type unions, maybe one would just rethink the type system. Or if you're okay with just type checking, that is that the inference wouldn't go very far, then it's probably just fine.
By the way, can't you just use a set?
Well, I mean, but the thing is like you say, okay, it's a set of like numbers and strings, right? Like you can do that in TypeScript, but you can't do that in Daphne, not without extra contortions, at least.
So,
right?
Can't I have like a predicate? Oh, sorry.
Yeah, I think that what you would do is you would have a data type, and the data type would be called something. Let's say you would call it JavaScript value or something, and then you would have a constructor for each of the types that you want. I mean that gives you a union. It's just that you need to construct and destruct the things all the time, which is not what one would expect from a union.
I think another corner case I ran into with this particular thing was when I'm actually building like a Daphne sort of a party-based testing system, and I was running into an issue of like having mutable objects, classes, and saying, oh, I want a class of A and class of B, and not just lumping them both into objects, because then that erases all their details and decrease sort of like you can say, okay, I can't say that this object's not in this other set of objects, right?
Right. So in that case, you may be able to use traits. So traits are abstract supertypes. So instead of going all the way up to object, you would have some trait. And traits can also be used as abstract supertypes of data types. So you can have a trait, right? The way that is set up right now is that well, I haven't checked for a couple months, but that you have to use 3 switches to get that, and that the intent is to switch to that by default, but I think that has not. I mean, everything that is sort of sitting there waiting for that to happen.
Yeah, Daphne hasn't had a release in a little while,
right?
So.
Or actually, wait a minute. Come to me. Did I?
Maybe.
Yeah. Or maybe it did
What does
change.
this
Anyhow,
do?
that's a different subject, maybe. But yeah. Abstemious. Right, that's off the subject. So abstemious, the word itself is the opposite of voracious. So voracious, you eat without, you consume without bound, but abstemious, you really try to cool it.
Very Puritan, okay.
Yeah. So what it means in terms of co-recursion is that you consume one thing, but you produce one thing. But it's not extensible to say that you consume two things and produce two things, for example. But that's what abstemious is. The best place to learn more about it is to search the Dafny test suite in the GitHub repository and see some examples.
That's how I found it. I was trying to do the multiplication of the power sums, and then that's the only thing that made it work. But then when I compiled to JavaScript, it never stopped. Like it could only produce one value.
Oh, okay. Actually, so in that case, the compilation may be buggy. But anyhow, yeah. But we're probably off topic from
yeah. I thought it was just my code bad, so I'm pretty sure it's just my code that is bad. So
okay, well, yeah.
So here are some abstemious. I don't know if this is what you meant, but like.
Yeah, this is all related to the co-recursive kind of stuff.
Right. So could you search for the word abstemious in that file? Oh yeah.
Oh, I see. Yeah.
So those functions are right. So for example, zip calls.
Yeah, that was the other thing. That was totally non-local. Like the zip was totally okay by itself, but when someone else was calling it or something like that, it was I had to put the subterminus.
Exactly. That's kind of the I mean the uncomfortable part of that that you could define, because if you have something else that uses zip, then because of the co-recursion, that really means that other thing is kind of part of the implementation of zip as well. I mean, which is not usually what happens when you, I mean, in procedural programming. But
sorry.
Yeah, so that's why it needs to be mapped. I mean, so different if there was something else like a sort of like a decreases clause, but a something that says how much it consumes and produces. That could do it. And there are things called
so
index.
like a graded stuff.
Yeah, maybe that's what some of them are called. And there are like wait, I was going to call them what are they called?
Is it what Granule doing, like when that it says like I am using this many times, and it doesn't say how many times.
Okay, I don't know about that work. I'm thinking about there's some work in the context of Agda. What are they called though? I was going to call them index types, but that's not what they call them.
It's okay. Yeah, Idris too uses them as well, I think, right? Can it be? Maybe okay. I wanted to also ask like this David Turner's, where it's like there's like this programming language where David Turner introduced total functional programming. He was able to get around this without using any flag. But it's probably due to his language being very, very simpler than Dafny, right?
It could be, right. So the abstemious also comes from, so Dafny had something that was called, it was called friendly, which actually just meant continuous, but we didn't use that word at that time. And then some people, Jasmine Blanquette and friends, did something in the context of Isabel, and they introduced what they called friends. And so if I remember correctly, abstemious is like their friends one, I think.
Thank you. I will definitely search them.
But I think abstemious is such a cool word that it should be used more often. I don't know.
We did search it on the Wiktionary to learn the meaning, like during the Berlin meetup.
Yeah, right. Yeah. Right. Oh, okay. Good. Yep. Yep.
Excellent. Anybody else have questions or anything else for Nana?
Can we also have the links for the projects that was shared? Like, I think I'm assuming they're already on the GitHub. Like, but
Yeah. Yeah, sure. I can. How should I send them? Should I?
We can just put them in the chat and like.
Okay. I guess I can. Can I give them to you afterwards, or because I don't really like. Let me see.
I'll go ahead and I'll post a few in the chat here. I already have them pulled up.
Okay,
And
great.
then we
Okay, because
can
I don't really.
also.
I mean, let me see. I can post my tabs in the chat. So wait, how does this work? Let me stop sharing, maybe.
Yes, that will help. But I've got the LemmaScript, lemmafit, dafny-replay.
Okay, and then there's
I think
a lot of the case studies are just on Midspiral, and like so for example the Hono example is there, the cookie, the let me just yeah, so here's one of the examples, and there's a lot of other LemmaScript projects over there, and you can look at the LemmaScript files. Like for each project you can basically look at the at this file there to see what has been actually changed, or you can look at the diff, but there's just
Yeah, maybe I have one more question.
Mhm.
What happens kind of about the TypeScript to Daphne/Lean conversion? What happens to numbers?
Yeah, so right now numbers are it's not they're not like they're not treated specially to deal with overflows and everything. So that would be one thing that we would need to do to be faithful there, to create a like. So for now we're just treating we're just doing it assuming that a JavaScript number, if it's an int, goes to a Daphne int or a Lean int, and that's a bit of a approximation there. Yeah, but if you have a JavaScript number, you can like type it to be either an int or a real or something, so that it's treated in the right way.
Okay, so that's also a comment or annotation in the.
Yeah.
Okay.
A different way to do it in Daphne is to use a new type and restrict the range of the new type to be that of a JavaScript of the integer portion of a JavaScript, which is essentially a 52 or 53, I can't remember, 52 53-bit number. And if you do that, then Daphne will recognize that number is, well, first of all, it will treat it with a range. But when you compile the Daphne, it will realize that range is something that fits within the integer portion of JavaScript's integers, and then it will compile it into a JavaScript number.
Okay, yeah, that sounds like a neat way to do it, yeah.
Right. There are many examples of doing that for, let's say, 8, 16, 32, 64-bit integers, but it also works for the 52-bit integers or 53, whatever it is in JavaScript.
Okay.
Yeah.
It looked like there was also like in the new Daphne version that hasn't been released yet. It looks like you've added an IEEE 754 like JavaScript like type explicitly.
There are floating point numbers right now.
Point
yeah,
types.
exactly.
Sorry,
yeah,
that's
right.
what I meant.
Which indeed, someone wanted to add that actually there were some good reasons for it, but I have no particularly good hopes that you could actually, verify things with it. It's too easy to prove that you don't get not the number and things like that. It will be hard work. But yes,
Okay.
it does exist, and it goes through because Boogie supports it and SMT supports it.
You also mentioned that the traits also work for data types. Is that like Rust traits, or like can I make like this Haskell traits hierarchy?
They are similar to Java's interfaces, similar to Rust's traits, and similar to Haskell's type classes, but they're not exactly the same. And but I think actually that they are on by default now. But they're not. But you don't get them from the IDE because I think that the new version of the IDE doesn't pick up on those yet. But if you want to, I'll type in the flags that you need.
Thank you.
A sort of related question to that is one thing we ran into while we were playing around was trying to rebuild Haskell's sort of monadic hierarchy, is that we could not figure out how to do an object or a trait that had two parent traits, and we're not like it basically had to be like a straight line in hierarchy, right?
Yeah, we were using modules, but then didn't you kind of figured it out a way out of it?
I don't think we ever did. We couldn't say that something was like traversable and like a monad, for example. Like I think we didn't. You had to do like explicit instances of each one by building the whole tree, basically. But they couldn't. There was no joining them together.
So a type can have two or more parent traits. However, those parent traits are not allowed to share the names of the methods. So if you have a method M coming from one trait and a method M coming from another, that's not allowed.
It might be probably good idea to add that we weren't using traits, but we were using modules to simulate the Haskell traits. Type, not family.
Yes.
Type class hierarchy.
Right. Yeah. That's what we were doing.
Mm-hmm.
It was modules. Okay, but yeah, maybe with this new trait system on data types, maybe we should give that a try again.
Mm-hmm. That sounds like a nice avenue to try it out on the next meetups.
Cool. Well,
and we should definitely try out this generating. That was so cool. Like doing the induction. Do I need the Claude Code for it, or can it also? It cannot do it manually, right? Or is it smart enough to do
the sketcher?
Mm-hmm.
The sketcher is completely symbolic. It doesn't use Claude Code.
Oh, that's cool. Okay.
Yeah, so it's really just piggybacking on the Dafny compiler. Actually, let me put the link. So it's piggybacking on the Dafny compiler, and it's it's basically like traversing a data type to make sure to know what all the cases are and things like that. Yeah.
And it works from the CLI as well, right?
Yeah, it does. There is a way to get it to work from this.
Thank you.
Yeah, let me know if you tried or if you have some rough edges that you want to see fixed or something.
Well, I will definitely try that. I made like this topology thingy. How do you call it? There was like this nice problem that I had when I was kicked out of the university and had too much free time. It was like this: could you write all the topologies on a finite set? And then I had like these two algorithms. One was running like double exponential, and the other was like just exponential. And now using LLMs, we were able to write that in Dafny. But the proofs are so long and unnecessary in some parts. So it could be actually cool to use the sketcher to just write the induction hypothesis and then like do it by hand. Trying to do that. But, yeah.
Cool. We'll see if it scales to that. Yeah.
Awesome. And just I guess we're probably a little bit over time, but that's fine. Is there anything else you want to finish up with, Nada, or
no? I think that's fine. I conveyed conveyed a bunch of stuff. It was an interesting discussion, cool discussion. So that was great. Thanks.
Awesome. All right. Any other comments before we wrap up? Okay, well, thank you all for coming. It was a lot of fun. It's very cool. Looking forward to hearing more about this project in the future. I'll keep trying it out myself. Yeah.
Yeah, thanks for your pull requests. I'll take a look now.
Awesome. Cool.
Yeah. All right. Thanks again. Bye-bye.
Bye-bye.
Thank you.
Bye.